All right. So it remains to show that, okay, we established hiding, right? Now we want to establish statistical binding. So to this end, we first start with, oh yeah, so that's the theorem statement that the construction actually satisfies the sum binding definition that we had. Maybe it's a good idea to pull the definition. So let's do that. Let's get the definition 3 point. Where is it? Okay, so this is the definition of sum binding. Let me copy it for you. There's this part. Okay, and then there's this part. Okay. All right. Oh, I actually don't know how much it recorded, but let's because I didn't actually do much. I thought it had started recording, so I'm sorry if I'm repeating a little. Feel free to skip ahead. Okay, so what we're going to now do is show that the construction satisfies statistical binding. We already show computational hiding, so that part was so that part is done, and the statistical binding is going to be actually just this much, right? It's very simple. So here's the proof. So first we recall that the fidelity between two states rho and sigma is given by this expression, right? So it's a trace of root sigma whole root trace squared. Okay. And we recall the definition of sum binding, so we have it right here, ready for us. And we note that the probability P sub B can be written as follows, right? So this is exactly what we had written in the definition, where remember the adversary is running some general attack by choosing some general psi and these unitaries to run the attack. Okay, and so this is the expression. This we can write as a fidelity, right? Because fidelity, remember, if sigma is pure, then one can write it as the inner product between the pure states. So we use that to write it as fidelity here. And then we use the fact that if you trace out some subsystems on both sides, then the fidelity increases, right? Because you're losing information, so they seem to be closer. Okay, and so because you get it at this point. So the advantage here is that you get both R and E in the trace, and when you have both R and E in the trace, this unitary can commute it and cancel it. Commute it, move it, cyclicity property of the trace. And then we have this expression, right? And now what we can do is we can write the sum of P0, P1 as 1 plus the fidelity between when psi is 0 and when psi is 1. Why that is because the sum of fidelity of rho zeta and sigma zeta xi, oh, this is I, sorry. Rho xi plus sigma xi is at most 1 plus f rho sigma, right? And rho sigma here in the psi 0 and psi 1. And zeta is capital psi with the trace. So we have this expression. And now we can just use the definition of what psi 0 and psi 1 were, right? So psi 0 itself was just the pseudorandom state, and psi 1 was the pseudorandom state conjugated with xz. And then we know from the lemma that if you conjugate with xz and you have uniformly chosen x and z, then this thing is just identity. It's an m-qubit identity, so identity and by the normalization. And okay, so the other part is exactly the same. Now we can assume that this state can be diagonalized, right? It's a density matrix, so we assume that the diagonalization is given by lambda I. And then this is identity, so you can also write in the lambda I basis, and then you can expand fidelity, and you'll get this expression. And now we can right? And this is a diagonal matrix of the one norm is, so this is simple. Now we get this expression. Now one can run Cauchy-Schwarz, right? Which is just A dot B is at most norm may not be, unless I miss some squares. Oh yeah, I missed some square root too. So you basically you run Cauchy-Schwarz, and then you're able to show that this would be at most the norm of this vector and the norm of that vector and the norm of vector with these entries, basically. And this is going to be 1, right, because of the fact that we assume that it's a diagonalization of a density matrix, and that's traced to 1. So the trace has to be 1. And so this part is fine. And then the other part you have to sum from I from 1 to zeta. And zeta can be at most 2 to the n. And right, because it's spanned by phi k, so it has at most those many independent degrees of freedom. So it's going to be at most 2 to the n. K was, remember, an n-bit string. And then you plug it in and you use the fact that m is at least c times n for some c is strictly greater than 1, and you get that the sum of the probabilities P0, P1 is at most 1 plus negative. Okay, and that completes the proof of sum bind. So yeah, that's how you construct a commitment scheme from a pseudorandom generator, which is secure for 1 copy. Yeah, sorry, finding the stop button takes a while. Okay.